All right, let's dive in. Today, we're going to pry open one of the most important black boxes in modern technology, deep learning. It is the engine running under the hood of so many things we use every day, from self-driving cars to incredible medical breakthroughs. And by the time we're done here, you're going to have a solid grasp on how it all actually works. So, let's get into it. So to kick things off, let's just ask a really simple question you've probably wondered about. How does a self-driving car tell the difference between a stop sign and, say, a pedestrian? How does it actually see the road? Well, the answer is a technology called deep learning, and we're about to break down exactly how it pulls that off. But first things first, we need a map. You hear these terms thrown around all the time: AI, machine learning, deep learning, and people often use them like they're the same thing. They're not. So to really get what deep learning is, we gotta see where it fits in the big picture. And this diagram lays it out perfectly. Think of artificial intelligence as the huge, overarching dream of making machines smart. Now, within that dream, you've got machine learning, which is a specific approach where we get systems to learn from data instead of just programming them with rules. And then, as a specialized part of that, you have deep learning, a super powerful technique that uses a particular structure to learn from absolutely massive amounts of data. So what's the secret sauce? What makes deep learning so special? Well, the answer actually starts with a design that's been around for billions of years: the human brain. The people who pioneered this whole field looked right at nature for inspiration to build a totally new kind of computing. Inside our heads, we have literally billions of these things called neurons. They're just tiny little biological cells, all connected in this vast network, firing signals to each other. And this massive, complex web of communication is how we think, how we learn, how we see the world. So scientists took that incredible biological blueprint and created a mathematical version of it, the artificial neural network. It's a system of interconnected nodes, these digital neurons that process information in a way that's directly inspired by our own brains. So just how powerful is this digital brain? Well, this quote kind of says it all. It gets at an idea called the universal approximation theorem. And what that means, in plain English, is that a neural network can, in theory, learn to model any pattern, no matter how ridiculously complex it is. From spotting a cat in a video to predicting the stock market, the potential is just about limitless. Okay, so where does the deep part of deep learning come from? It's actually way simpler than it sounds. A deep neural network is just one that has a bunch of layers of these artificial neurons stacked between the input and the final output. It's these extra hidden layers that let the network learn patterns at different levels of complexity, which is what makes it so incredibly powerful. So, we've got our artificial brain, fantastic. But how does it actually, learn? Well, it's not magic. It's this really elegant 4-step process that just repeats over and over and over, getting a tiny bit smarter with every single loop. This is the core learning cycle, and it's got 4 main steps. First, the network makes a guess. That's forward propagation. Second, it figures out how wrong that guess was using something called a cost function. And finally, it uses that error to learn from its mistake and adjust itself through back propagation and gradient descent. Let's walk through that. Everything starts here. We feed some data, like a picture, into the very first layer. That information then flows forward from one layer to the next, with every neuron doing a quick little calculation, until finally it spits out a prediction at the other end. That's its first guess. Now, if we zoom in, this is what's happening inside each one of those little nodes. It's taking in signals from the layer before it, but not all signals are treated equally. Each one has a weight, and you can think of that like a volume knob that determines how important that signal is. The neuron adds up all these weighted signals, and if the total is high enough, it fires and passes the message on to the next layer. Okay, so the network made a guess. But was it right? Probably not, especially at the beginning. The cost function, sometimes called a loss function, is just a way of measuring the error. It calculates the gap between what the network predicted and what the right answer actually was. A huge number means it was way off. A small number means it's getting closer. So how does the network use that error to get smarter? This is the most brilliant part. A process called back propagation sends that error signal backwards through the network. It's like a detective tracing the mistake back through every layer to figure out which connections, which of those little volume knobs, were most responsible for the wrong answer. Then gradient descent comes in. Think of it like this. You're a hiker on a foggy mountain, and you need to get to the lowest point in the valley. You can't see, so you just feel the ground around you and take a small step in whichever direction goes down the steepest.
That is exactly what gradient descent does. It slightly adjusts all those little weights to make the error just a tiny bit smaller. And this whole loop repeats thousands, millions, even billions of times, with each cycle making the network just a little bit better.
All right, enough theory. Let's connect this all back to our self-driving car. How does this whole process actually let a computer recognize what's in an image? This is probably one of the most powerful and easy to understand applications of deep learning. Now this right here, this is the absolute game changer. With older methods of machine learning, a human programmer had to do all the hard work up front. They had to tell the machine, hey, if you want to find a cat, you need to look for pointy ears and whiskers and a tail. With deep learning, you don't do any of that. You just show the network thousands of cat pictures, and it discovers what those important features are all by itself.
And the special type of deep network that's just ridiculously good at these kinds of vision tasks is called a convolutional neural network, or CNN for short. Its whole architecture is specifically designed to work with grid-like data, which is exactly what the pixels in an image are.
A CNN basically works in two stages. The first part is like a detective, the feature extractor. It scans over the image and learns to identify all the key patterns, little things like lines, curves, and textures. The second part is like a judge, the classifier. It looks at this whole collection of features that the detective found and makes the final call. Cat, dog, stop sign. So, just to put it another way, the first half of the network is the feature detector. It learns to spot edges, shapes, colors, and eventually more complex stuff like eyes or wheels or letters. The second half is the decision maker. It looks at all the features that were just found and says, okay, based on everything I'm seeing, this is definitely a picture of a stop sign. And here's the thing. This incredible ability to learn from data isn't just for seeing things. Not even close. Deep learning is a general-purpose tool, and it is fundamentally changing dozens of industries. It really is everywhere. Its most obvious impact is in computer vision. It's the tech that unlocks your phone with just a glance, the tech that helps doctors spot tumors in medical scans, and yes, the tech that guides that very self-driving car we started with. But it's also completely revolutionizing how we interact with language. You know those real-time translation services that feel like pure magic? Or your email spam filter that just knows what's junk? Or the chatbots that actually understand what you're asking? Yep, that's all powered by deep learning. And its impact goes even deeper, right into the heart of science itself. Researchers are now using deep learning to speed up drug discovery by predicting how different molecules will interact with each other, a task that could save years of lab work and potentially save lives. So we've gone from the idea of a single biological neuron all the way to an artificial brain that can see, read, and even help discover new medicines. This is really just the beginning, and its potential is just staggering. So the real question isn't just what it can do, but what we should do with it. As this thing gets smarter and smarter, what's the one problem you hope it solves next?